This is an image of Sagittarius A*, the supermassive black hole at the center of our Milky Way galaxy. Black holes themselves don't emit light, so what we're actually seeing here is the hot, glowing plasma swirling around it. This is only the second direct image ever captured of a black hole. It was produced by the Event Horizon Telescope, EHT, collaboration, the same team that released the first image of the black hole in galaxy M87. Originally, Sagittarius A was the main target, since it's located in our own galaxy and is about 2,000 times closer to us than M87. But it's also more than 1,000 times smaller, so it appears only slightly larger in the sky. Capturing an image of it came with unique challenges. For starters, there's a lot of dust and gas between Earth and the galactic center, which blocks visible light. That's why astronomers had to use infrared and radio wavelengths to see through the clutter. Over the past 30 years, astronomers have been closely studying the center of the Milky Way. They've tracked stars orbiting rapidly around something massive but invisible. One of those stars has been clocked moving at 24 million meters per second, about 8% the speed of light. All of the stars seem to orbit a compact, heavy object that gives off very little light. Occasionally, it flickers faintly. That object is believed to be a supermassive black hole, roughly 4 million times the mass of our Sun, squeezed into a single point called a singularity. Anything that crosses a certain boundary, called the Schwarzschild radius, can't escape, not even light. So, the radiation we detect actually comes from material farther out, usually from superheated plasma spiraling into the black hole. Sagittarius A is relatively quiet, meaning it doesn't consume much matter. On the other hand, M87's black hole is far more active, pulling in gas from its surroundings. Since M87 is over 1,000 times larger, it changes more slowly, which made it easier to image. In contrast, Sagittarius A changes on the scale of minutes. Visualizations created by researchers like Luciano Rezzola at Goethe University Frankfurt help illustrate these differences. But the biggest challenge in imaging any black hole is its tiny apparent size from Earth. To get a sense of scale, the entire night sky spans 180 degrees. The Andromeda galaxy stretches across about 3 degrees. By comparison, Sagittarius A takes up just millionths of an arcsecond, about the size of a donut on the Moon as seen from Earth. No traditional optical telescope on Earth could capture something that small. So, how did scientists do it? And what exactly are we looking at in the image? Let's break down how the image was made. The EHT used radio waves with a wavelength of 1.3 millimeters, detected by a global network of radio telescopes, large, dish-shaped antennas that scan the sky. When one of these telescopes locks onto a radio source, it receives strong, in-phase signals, producing a bright spot. As it moves off target, the signals fall out of phase and cancel out, causing the brightness to fade. The sharper this contrast, the better the resolution. There are two ways to improve resolution: use shorter wavelengths or increase the size of the telescope. For imaging black holes, increasing the effective size is more practical, since shorter wavelengths get blocked by the atmosphere or by the black hole's own surroundings. To clearly resolve the black hole's features, scientists needed a resolution high enough to distinguish the bright ring from the dark center. But no single telescope could provide that. The only way to get that level of detail was to create a virtual telescope the size of Earth. While building such a telescope isn't possible, scientists achieved this virtually using a method called Very Long Baseline Interferometry, VLBI. Instead of using one massive dish, the EHT team combined data from multiple radio telescopes across the planet. These telescopes observed the black hole at the same time, recording enormous amounts of data with extremely precise timing, down to the femtosecond. The datasets were so large that they had to be physically shipped on hard drives to central processing facilities for analysis. When telescopes are spread across Earth, the time difference in receiving the same radio wave helps pinpoint its source. If two telescopes receive the wave at the same time, the source must lie somewhere equidistant between them, forming a line of possible locations. Because radio waves repeat every wavelength, there are multiple possible positions where the paths differ by whole wavelengths. This creates interference fringes. The more telescopes you use in different locations, the more of these fringes you can analyze. By combining all that information, scientists reconstructed the image. So, what does the image actually show? At the center, there's a dark region, the black hole's shadow. This marks the event horizon, the boundary beyond which nothing can escape. But the shadow appears about 2.6 times larger than the actual event horizon. Why? Because space-time around a black hole is warped. Light paths bend dramatically. Even rays that come in slightly above the event horizon still get pulled in. To reach us, light must come from at least 2.6 Schwarzschild radii away, grazing the photon sphere, where light can actually orbit the black hole. What we're seeing, then, is the shadow of the photon sphere. It's not just a dark spot from light being absorbed, but a gravitationally lensed silhouette created by extreme light bending. In fact, the warping of space-time lets us see light from behind the black hole curved all the way around it. So we're not just seeing the front, we're seeing a warped image that includes its backside, too. Surrounding the shadow is an accretion disk made of superheated gas and dust. This disk doesn't reach all the way to the event horizon. It ends at the innermost stable circular orbit, about 3 Schwarzschild radii away for a non-rotating black hole. Light can orbit even closer, at around 1.5 Schwarzschild radii, but those orbits are unstable. Thanks to gravitational lensing, we can still see the backside of the disk, even if we're viewing the black hole from an angle. Light from behind the black hole curves around and reaches us, creating a glowing ring. It's similar to what was depicted in the movie Interstellar. There's another effect at play: Doppler beaming. The gas in the accretion disk moves at speeds close to the speed of light. The side of the disk moving toward us appears brighter, while the side moving away appears dimmer. That's why the ring in the image looks asymmetrical, brighter on one side. In the end, what we're seeing isn't the black hole itself, but the bright, glowing ring of plasma around it and the shadow it casts. It's a remarkable snapshot made possible by an extraordinary global effort, radio observatories working in sync to capture one of the most extreme and mysterious objects in the universe.